Okay, we go. All right, welcome to Double Slit 3. It's Double Slit Experiments 3, Delayed Choice. I'm Robert Nemeroff. This is Michigan Tech. And this is going to be a fun one, so you might want to bat down the hatches, put on your seatbelts for this one. So this course is officially titled Extraordinary Concepts in Physics. It's being taught at Michigan Technological University in the beautiful Upper Peninsula of Michigan. I try to be light on math and heavy on concepts, but anyone, anywhere is welcome. There's no textbook, it's all Wikipedia. You can find the lectures online. You probably found them online already or you wouldn't be watching this. However, if for some strange reason this showed up and you don't know where this came from, if this is taking control of your monitor, you might want to go to Starship Asterisk, which is a discussion board for Astronomy Picture of the Day, and search out for Physics X, and you will see all the lectures. That's at Google or a similar search engine. However, if you can read this fine print here, which came out smaller because for some reason Google Docs has been changing fonts on me, occasionally, not consistently, or I'd correct it, you can go to that address and find the lectures listed there. All right, so one of my favorite ways of doing things is coming up with experiments, because experiments are at the root of physics. If you can predict the results of all experiments, then you don't need anything else. You're an oracle of the physical world. Studying the results of experiments are fundamental. It's something that's very basic. Mathematics can be interpreted, and I guess the results of experiments can be interpreted in terms of mathematics, but the whole idea of physics is to create the ability to predict the results of specific experiments. For instance, why buildings don't fall down and bridges and things like that. All right, so let's go to the double slit experiment, which is really strange. And the usual double slit experiment is done. And if you want to know what that is, go back to the past lectures, double slit experiments 1 and 2, particularly 1. It will tell you in lurid detail what I mean by double slit experiment. It's done, except now the screen containing both the slits is tilted. So you have a source here of light. You have a single screen here that now has 2 slits, and this is your slit screen. This is your image screen. So I write right on top because I find people can still understand things. Let's say you tilt this. Now previously, when it wasn't tilted, when things were in red, it was untilted and you got an interference pattern. But now you tilt it. If you tilt the slit screen, do you still get an interference pattern? No, the interference pattern must disappear because it's highly dependent on exactly the distance between here and the 2 slits. The second answer would be a normal interference pattern would appear. The image screen for some reason might go mysteriously blank, or the slits slide off the slit screen. You forgot to secure them. Which one would it be? So please pause and contemplate this for the rest of the year. So coming back next year, here I am. It's next year, and here's the answer. A normal interference pattern appears. So an interference pattern will appear that is normal but shifted from the pattern that would appear for a non-tilted slit pattern. The single slit peaks would appear in their non-tilted locations, however, as they are still the projection, at least the centers of them are the projection of the light onto the image screen. So that was again, one of the things I'm trying to do is take the single slit experiment and start changing stuff, one thing at a time, and see what happens. That's how I understand stuff. So hopefully that will affect you too. Okay, now we're going to do something a little bit stranger. It's called quantum eavesdropping. This is a classic 2-slit experiment. Sometimes there are debates as to the details of how it should go, but here we go. The usual double slit experiment done, except now using electrons. We can do that. That was a lecture ago, I believe. And now you illuminate both slits with photons. And the photons have sufficient energy to discern which slit each electron went through. So now, before you had your classic double slit experiment with electrons. Now you illuminate the electrons and you say, aha, I now know that this electron went through that slit. And I now know that the next electron went through a different slit. Does this affect things? Do you get no interference pattern? Do these photons take out the interference pattern? Do you just get your normal interference pattern? The electrons just don't care? Or do you see the image of a single electron fluctuating, and therefore maybe you can put that on the magazine or something? What is it you see? Okay, so we'll wait again until next year. Contemplate this. You can whistle Jeopardy music to yourself. I find that effective. No interference pattern appears, a classic experiment in physics. If you determine which way, which path information it is that the electrons go through, that will wipe out the interference pattern. The weird thing is if you take the photons down so that there's so less energy that you can't tell from the photons where they came from, so you don't know which slit the electron went through, again you recover the interference pattern. Once the photons become energetic enough, you lose that and the interference pattern goes away. So we're going to be dealing a lot of these type situations. It's called quantum eavesdropping because one of these things, one way to use this kind of stuff, this stuff could have some minor uses, is to find out if someone is checking on the results of your experiment. If anyone knows which slit the electrons went through, if they really know, that's going to wipe out the interference pattern. So if you're at the end of the experiment and you see no interference pattern and you thought you would, then maybe there's quantum eavesdropping. Maybe somebody's listening in on your conversation, your electron conversation. All right, so let's go to bad eyes. Usual double slit experiment is done, back with photons, except now a human places one eye in front of part of the image screen. The eye is small compared to the previous interference fringes and too blurry to see each slit independently. The person is therefore not able to say which slit each photon went through. So let's start on the other side now. Here you have photons coming out. Here you have your double slit screen. Here you have your image screen. And then you have a person show up here with an eye. I missed it. I have to put the eye in another color so you can see it. They have a red eye, not pink eye. This is not, we're very clean here. So what happens? Does this person see part of the interference pattern? Because before there was an interference pattern, which I'll cartoon draw like that. Do they see part of a no interference pattern? Does the image screen go blank? Or do you need glasses? Is this an indication you just need to go to the optometrist? What happens if you go in front of the screen and you look toward the slits, but you just can't make them out? And the answer, please. The answer is not good. Let's see. Hit the wrong button. Sorry. Please stand by. We're experiencing technical difficulties. Okay. The answer is that person sees part of an interference pattern. Specifically, the person sees the part of the interference pattern that would have occurred on the image screen directly behind them. So their fuzzy eye is now, it's like it's part of the image screen. And so if it was dark back there, then they just see darkness. And they say, oh, you should turn on that laser. If it was light back there, they say, oh, I see light coming from the direction of the two slits, but I can't tell you which slits they are. So now that person invites their friend. Their friend has a larger eye. And their friend has great vision. Their friend repeats the experiment, except now they can see well enough, good enough, to see each slit independently. And if you can see each slit independently, you can tell which slit each photon goes through. Supposing now, let's say the photons are just reduced to one photon per shot. So you say, oop, that one came through the left slit. Oh, there's another one. Right slit again, left slit. And they know. So then this person's going to know which slit each of the photons went through. What do they see? Do they see part of an interference pattern? Do they see part of a no interference pattern? Does the image screen remain blank, or do they go blind just like their mother warned because you're looking at laser light? If you read the warnings, you shouldn't do that. So after this experiment, they're going to have a bad eye. But for the sake of the experiment, let's say the eye remained good the entire time. Contemplate that. What happens? The person sees part of a no interference pattern, and this one took a while to figure out, actually. First of all, the person knows which slit the photons went through, so that's going to break off the interference pattern. But here's the weird thing. If you look behind them, you would see, if they're in front of a screen that's showing an interference pattern, and they're showing up here, and their eye sees part of a no interference pattern. How's that? Well, it took a while for me to understand. The eye is large enough so that on the eye there's light and dark fringes. And all together, washes out and the total brightness the eye sees is consistent with the no interference pattern. So you can't just go behind it with good eyes and say, oh, I'm going to stand in a minimum. No. If you're going to resolve the slits with your eye, you have to see both maximum and minima. And that's the way that works. So these are attempts to defeat the two-slit experiment. You've defeated the two-slit experiment if you get an interference pattern and you know which slits the either electrons or photons went through. So far, well, no one's been able to do it. And a lot of people have tried. So it's a little bit like that sword in that thing where you have to take the sword out of the rock. It's a little bit like that. We're still waiting for somebody. All right. And I'm sure there's lots of knights out there who want to try. So here we go, delayed choice. So the usual double slit experiment is done again, except now a person with large but blurry eyes stands in front of the image screen. The observer cannot resolve the slits. With glasses, however, the observer can resolve the slits. A bunch of photons are emitted from the source. The observer is allowed a delayed choice about whether to put the glasses on after a group of photons has passed the slit screen. So I'm actually going to skip through this because we're going to go through this. So I'm short on time. And so what would happen? The person sees an interference pattern, no interference pattern. What the person sees depends on the observer's choice, or saying E equals mc squared makes the person feel smart. So the person will always see no interference pattern and for the explanation there, but I'm running short on time. So I'm going to get right to the polarized slits experiments. So this will be covered next time too. The usual double slit experiment is done, except now a vertical polarizer is placed directly after one slit, or before actually, while a horizontal polarizer is placed directly after the other slit. So here you have this slit screen. A polarizer you can look up by clicking on this link. And so here you have now something here that makes the photons horizontally polarized and something here that makes the photons vertically polarized. What happens? Before you put those polarizers there, you would get an interference pattern. But now, do you not get an interference pattern? Do you get something that looks like this, no interference? Or do you get a polarized picture of the observer? Which is that? Okay, so actually I can click to the next one. No interference pattern appears because the polarizers allow you to tell which photons went through which slit. If it's horizontally polarized, that photon went through the horizontal polarization slit. If it's vertically polarized, it went through the other one. So each photon is now tagged by the polarizers, and you can tell. And when you can tell, you do not get an interference pattern. So it changes just like that, zoop. Which path information will destroy the interference pattern? All right, 2 minutes. I got my 2-minute warning. Okay, quantum eraser. Let's say you now have the same thing. You have the two things, except here this is the horizontal, this is the vertical. Now, however, you place another one that rotates them all by 45 degrees. Therefore, all the photons, regardless of whether they were horizontally polarized or vertically polarized, they now have been switched to 45 degrees. What happens then? No interference pattern, a normal interference pattern, or the electrons now appear wearing sunglasses. And I got to go quick because I'm within 2 minutes. A normal interference pattern reappears when you put in the other polarizer. You can reconstruct the interference pattern after the slits by putting in a third polarizer. That again makes it impossible to tell at the image screen what's going on. Okay, it gets better. Here's the conclusion. Let's say now that you'd redo this experiment, except you stand here with a third polarizer, and you have the ability to deploy that or not deploy that after the photons have crossed the slit screen. So the photons have crossed the slit screen. People would have thought they would have done what they're going to do. But now, at the last minute, a bunch of photons all run at the same time. You can deploy the polarizer or not. What happens? Do you always get an interference pattern? Do you sometimes get an interference pattern, never get an interference pattern? Or does it depend on the choice of the observer to deploy that or not? Can the observer deploy something that creates or destroys an interference pattern? And the answer is, what the person sees depends on the observer's choice. This is the famed delayed choice quantum eraser. You as the observer can put on glasses that determine whether you see an interference pattern or not. And this is one of the strangest results in quantum mechanics. This is delayed choice quantum, and we will talk about this a little bit next time. But I'll end with a Feynman quote. If you think you understand quantum mechanics, then you don't understand enough to understand that you don't understand it. Talk to you next time. You might want to go to Starship Asterisk, which is a discussion board for Astronomy Picture of the Day, and search out for Physics X, and you will see all the lectures. That's at Google or a similar search engine. However, if you can read this fine print here, which came out smaller because for some reason Google Docs has been changing fonts on me, occasionally, not consistently, or I'd correct it, you can go to that address and find the lectures listed there. All right, so one of my favorite ways of doing things is coming up with light on math and heavy on concepts. But anyone, anywhere is welcome. There's no textbook, it's all Wikipedia. You can find the lectures online. You probably found them online already, or you wouldn't be watching this. However, if for some strange reason this showed up and you don't know where this came from, if this is taking control of your monitor, Experiments 3, Delayed Choice. I'm Robert Nemeroff, this is Michigan Tech, and this is going to be a fun one, so you might want to bat down the hatches, put on your seatbelts for this one. So this course is officially titled Extraordinary Concepts in Physics. It's being taught at Michigan Technological University in the beautiful Upper Peninsula of Michigan. I try to be Okay, we go. All right, welcome to Double Slit 3. It's Double Slit